All right, everyone, we're going to be talking about Newton's second law today. So Newton's second law is that big equation that you've probably heard of before. Our force is equal to mass times acceleration. Now, a lot of the time you will see this law written like this. So this sigma right here, you probably learned from your math class. It's a sum notation. It just means the sum of the forces or the net force. You add them together. Now, force, just like acceleration here, is a vector, which means that it has a direction. So that means that you want to call one direction positive, one direction negative, and then add up your forces accordingly. You can also see the notation written like this sometimes, F sub net. That's the same thing. Whatever floats your boat, you can use either one. A lot of the time I will use the sigma. Now, the way that Newton actually wrote this equation was A is equal to force divided by mass. And the reason that this notation is good to think about is because we can see how force and mass affect acceleration. So we can see that since force is on the numerator here, it's going to be directly proportional to acceleration. So because of that, that just means like the bigger the force, the bigger the acceleration. And that makes sense, right? If we push something harder, it's going to accelerate more. We can also see, since mass is on the denominator, that acceleration is inversely proportional to mass. So think about a big object and a small object. If you give them the same force, the bigger object has more inertia, so it's going to be harder to accelerate. So bigger the mass, the smaller the acceleration, and that makes sense. Now, the units for force are newtons. You see a theme here, Newton's second law. Units for force are newtons. And Newton is just a kilogram times meters per second squared. That's what that unit is made up of. So let's talk a little bit about the force of gravity, which is what we call the weight of the object. Okay, so the force of gravity on an object is equal to the mass of the object in kilograms multiplied by the acceleration of gravity. Now we know from kinematics that the acceleration of gravity on Earth is 9.8 meters per second squared. So that is your little g here. You'll see this notation a lot, little g. Whenever you see that, that's just the acceleration of gravity, which we know, again, on Earth is 9.8 meters per second squared. So this is the force that's causing an object to accelerate towards the Earth. It's causing us to stay on the Earth. The force of gravity of an object is also known as the object's weight. So this is why when we go to the moon, or astronauts go to the moon, I don't go to the moon, obviously, but this is why astronauts look like they're lighter on the moon, and it's because their weight is less, because the force of gravity is less on the moon, because the acceleration of gravity is less on the moon. It's about 1.62 meters per second, if I remember correctly. So this is why astronauts look like they weigh less on the moon. It's because they do. Now, when you go to the doctor and they get your weight, it's not always your weight. So if they're getting your weight in kilograms, it's not actually your weight, it's your mass. But if they're getting your weight in pounds, pounds is actually a unit of force as well. So this would be your weight. But kilograms, like I said, is a unit of mass. So mass is the amount of matter that your body is made up of, the amount of stuff your body is made up of. So that's not going to change. It's not going to change unless you eat a bunch of hamburgers or something like that and gain some mass, or you are training for a marathon and you lose some mass. Your amount of stuff won't change unless one of those two things happens. But your weight will change if you go to the moon, but your mass will not. So those astronauts on the moon, they still have the same amount of stuff that they had on Earth, but they weigh less, so they feel like they're lighter. Okay, so like I said, when you go to the moon, your mass doesn't change, but your weight changes because the acceleration of gravity is different on the moon. So let's go through some steps for solving Newton's laws problems. Number one, you want to draw a free body diagram. So if you have multiple objects, you will be drawing multiple free body diagrams. We will talk about a problem called an Atwood machine, where we have two masses that are connected by a rope over a pulley, and they move like this. So that's called an Atwood machine. There are two masses there, or maybe even more sometimes. So we will talk about what we do with those type of problems, what we do when we have multiple objects involved. Number two, if any forces are at an angle, we want to split those forces up into X and Y components. So just like we did with projectile motion, when we have stuff at angles like velocity in projectile motion, or here forces with free body diagrams, we want them in the same XY plane. So we need to split that angled force up into X and Y components so all of the forces are in the same XY plane. Number three, we then want to use Newton's second law in the x direction and y direction separately. So again, just like we did with kinematics, we split up that x and y direction separately. And then if an object is at rest or moving at constant velocity, remember that the net force is zero. So for example, if that object is just accelerating in the x direction, the net force is zero in the y direction because it's not actually moving in the y direction. And then finally, step four, we are going to use Pythagorean theorem and trigonometry if needed to find our answer. So sometimes we have acceleration in 2 dimensions, and we might need to use Pythagorean theorem for some, in trigonometry for some reason.